Good afternoon. We're going to discuss output response characteristics, Lecture 6 of Feedback and Control System. Our topics are poles and zeros, and we're going to discuss about the natural response and forced response and how our poles and zeros are plotted in the S-plane. Our second topic is time response. We are going to solve the time response equation, the output transform equation. We already know this. The input pole, the system 0, and the system pole. Our third topic is response characteristics. So we're going to discuss the first order system, and these characteristics are the time constant, rise time, and settling time. And we're going to evaluate responses as well. Our fourth topic is general response characteristics. This time we're going to discuss the second order system. We're going to identify first the underdamped, overdamped, undamped, and critically damped second order system versus the general second order system. On our topic 1, poles and zeros. After obtaining the mathematical models, the transfer function, and the state space representation of a subsystem, it is analyzed for its transient and steady state responses to see if these characteristics yield the desired behavior. And doing so, the poles and zeros are design tools to describe a valuable analysis of the mathematical model. Later on, by simply looking at the transfer equation, we might be able to describe the characteristics of our system. Once more, here is an example of our output time response. No? So the curve, okay, this is the response output of our RLC circuit, no? As what you've been doing in your laboratory activities. Let us recall that the output time response of a system is the sum of two responses, the forced response and the natural response. Poles and zeros is an analysis and design technique, a qualitative method of describing the output time response in minimal time and less laborious than mathematical models. So we have to take note that the natural response is the system's effect without the influence of an input or forced response. Before we further to our example of solving poles and zeros, let us first recall the different forced responses or input responses that we want to input to our system. We have an impulse signal, a step signal, a ramp signal, a parabola, or a sinusoid. These are the symbols of the functions. Okay, I believe we are very much familiar with this already. They're mathematical equations, no, to describe the function. And the sketches, so for the impulse, no, it's one pulse, no, okay, for one instant of time. For the step, okay, from a certain point of time, say 0, it steps from 0 level to high level. And for the ramp, it is a continuously increasing. For parabola, it has a parabolic shape, no, As time passes, the function increases in parabolic form. And of course, as we're very much familiar, the sinusoid. Okay? And in table 2.1, the Laplace equivalent of each of these functions. So poles of a transfer function are the values of the Laplace transform variable, which is s, no? The value of s from this transfer function that cause the transfer function to become infinite. Or any roots of the denominator of the transfer function that are common to roots of the numerator. Now, in our example, there are no common roots, but in case there is a common root, say for example, if this is s plus 1 and we have s plus 1 in the denominator as well, so there is a common root between the numerator and denominator, and it is also considered as pole. Now, in this case, as defined, that the value of s that makes the function infinite. So as we know in algebra, if the denominator of a fraction is 0, therefore the fraction will be infinite. So meaning to say this terms, no, or factors in the denominator, if we're going to equate this to 0, no, it will make the whole transfer function equal to 0. And therefore, this will be the values of the pole. -4, -5, and -8. Take note, by the way, that these are the roots, no, of the denominator. As we know in our transfer function, we have a polynomial in the numerator and a polynomial in the denominator, and we take the roots of the polynomial. So the poles are the roots of the polynomial that make the function equals to 0. The zeros of the transfer function are the values of the Laplace transform variable s that this time make the transfer function become 0. And likewise, if there is a common root in the denominator. So what makes the numerator equal to 0? So if s is equals to -1, so the numerator will be 0. Or if s is equals to -2, it will be equal to 0 as well. So our zeros for this given transfer function is -1 and -2. For our example, if we have this transfer function and s plus 2 over s plus 5, no, is our transfer function, the gs, and our input signal, take note, this is a step input, the 1 over s, if you recall from our previous slides. So we're going to have the equation of Cs to be equal to Rs times Gs, and Rs is 1 over s, and Gs is s plus 2 over s plus 5. So therefore, we could directly say that the pole is equal to -5, and the 0 is equal to -2. And for the s-plane, we use the symbol, this circular symbol for the 0, and an x symbol for the pole. Okay, so the intersection here is of course 0. Okay, so -2 and -5 here. So this is the s-plane. And once more, the Laplace from the table 2.1, the Laplace transform table. Okay, our input is the step function, no? Step response or step function. Okay, so that's all for our poles and 0, our topic 1. I want you to solve the poles and zeros of your laboratory activity.